Hello and welcome to a walkthrough of the Pearson Edexcel International A-Level Unit 5 that was sat about 2 weeks ago on Friday the 9th of June. 1 hour and 45 minutes. Starting with 10 MCQs. Question 1. The ultimate fate of the universe is uncertain. Which of the following would result in an open universe? If you remember the little graph in your textbook, there's open, there's flat, and there's closed. And it's all to do with the average density of the universe. If the average density of the universe is equal to the critical density of the universe, as per A, it would be called flat. But this is where the average density of the universe is less than the critical density, and therefore it results in an open universe. The answer is B. C and D are just red herrings. A hydrogen source on Earth emits a spectral line with a wavelength of 410 nanometers. An observer determines the wavelength of the same line in the spectrum of a star. The star is moving away from the Earth at 2.5% of the speed of light. What is the wavelength of the line as determined by the observer? So the change in length divided by 410 must be 2.5%. So it's going to be longer than 410. I mean, you could just do a trial and error. You could try 420, you could try 430, or you could work backwards. It really doesn't make a big deal. If I say 420, then that would be 10 nans divided by 410 nans. And 10 nans divided by 410 nans is pretty close to 2.5%. So the answer is C. Can't be A, because A would be coming towards you, and we're told it's moving away. So it'd be longer. So 2C. Trigonometric parallax. If you remember with parallax, the larger the angle of parallax, the closer you are. So we're told that star X has twice the parallax angle of star Y. That means that star X is closer than star Y, and that star Y is twice as far away, and that fits C. Very straightforward question. Question 4. A satellite of mass m is on the Earth's surface. The satellite is moved into a circular orbit of height h above the Earth. The mass of the Earth is m, and the radius of the Earth is r. Which of the following gives a change in gravitational potential energy of the satellite? So what you're looking at here would be the difference between the gravitational potential energy on Earth, which is big G, big M, little m over r. Take away the potential energy R plus H. So it's got to be B. What else could it be? It's not asking you for gravitational potential. It wants gravitational potential energy, so you're going to be multiplying by little m. So, yep, I think it's B. Moving on. Measurements related to a distant galaxy may be used to determine the value of the Hubble constant. If you remember, the Hubble constant is basically the rate of expansion of the universe in terms of the amount of the universe that's expanding per second, which is a bit weird, but that's what it is. The greater the Hubble constant, the faster the universe is expanding. So the two things that you need for your graph, if you remember, you need distance and you need recession velocity. So the answer is B. Buildings in earthquake zones often have a structure that includes ductile materials. These materials help to damp oscillations of the building during an earthquake. Which of the following describes a ductile material? This is like an IGCSE question. A ductile material means that it can have a large plastic deformation before it breaks. It's not about behaving elastically under tension, and it's nothing to do with C and nothing to do with D. It's to do with being able to stretch it into wires, if you remember. So the answer there is 6B. Question 7. A student is investigating the absorption of gamma radiation by lead. Before starting the investigation, she determines the background count. Interestingly, it says background count, not background count rate. So, which of the following does not affect the background count? Well, the count time would certainly affect the background count, because the longer you counted for, the larger the background count. The location can interfere with background count, and the type of detector you've got would certainly affect the background count you've got. The one thing that will not affect it is the temperature. So that's obviously 7C. Question 8. Mars has approximately 8 times the mass of the Moon. Mars has twice the diameter of the Moon. The value of G on the surface of the Moon is 1.6 newtons per kilogram. What is the value of little g on the surface of Mars? If you remember the formula, it's big G, big M over R squared. So the top, 8 times the size, it's going to be 8 times more because it's 8 times more massive. But on the bottom, you're dividing by the square of the radius. So it's going to be 8 on the top, 2 squared on the bottom, which is 4. So overall, it's going to be about 2 times more. So it's going to be about 3.2 HC. Question 9. 2 gas cylinders have the same volume. One cylinder contains nitrogen gas. The other cylinder contains oxygen gas. Both gases are at the same temperature and pressure. So if they've got the same volume, the same temperature, and the same pressure, PV on one side must be the same, because pressure times volume is constant. And pressure times volume equals nRT. We're told that T is the same, R is a constant. So N, the number of moles, must be the same. So the number of molecules must be the same. So each cylinder contains the same number of molecules. That must be true. The average molecular kinetic energy is the same for each gas. That is certainly true because they're at the same temperature. And the internal energy is the same for each gas. Well, that's the internal energy for an ideal gas. Is simply the kinetic energy of each gas. And because the temperature is the same, that would be the same too, because you've got the same number of particles. The one thing that won't be true is the density of gas. So the answer is 9C. Question 10. A particle is undergoing simple harmonic motion. The graph shows how the velocity v varies with time t for the particle. Now, which of the following graphs shows how the displacement varies with with t during the same time interval? Now, you've got to be careful here. This is velocity. It starts at 0. If velocity is 0, it must be at the end of a swing. It must be at maximum displacement. And then, if you notice, the velocity is positive and becoming a maximum positive value. Now, I reckon that must mean that you must start at a negative maximum displacement, because then you would then move forward, and then after a short while, you'll have maximum positive speed. So the one that fits here is B. It can't be A, because that's starting at 0. It can't be C, because that's starting at 0. The question really is it B or D? Well, if it was D, wouldn't the velocity be negative for the first bit? And we're told the velocity becomes positive. So I think it's B. Excellent. So those are 10 straightforward MCQs. Question 11. A nucleus of rhenium-187 decays to a nucleus of osmium by emitting a beta- particle. Complete the nuclear equation for the decay of rhenium-187. Goodness me. Besides some neutrino, this is very much an IGCSE question, isn't it? So you know it's beta- particle. The number on the top isn't going to change. The number on the bottom is going to go up by 1 because the neutron is turning into a proton. And you need to know that a beta minus by convention is 0 on the top and -1 on the bottom. And if you add them all up, left and right, they all balance. So there you go. 11b. The energy released in the decay is 2.6 kilo electron volts. You may assume that, in this case, the beta particle receives all the emitted energy. Calculate the speed of a beta minus particle emitted in this decay. So all we do is we turn the 2.6 keV into joules by multiplying by 1.6 times 10 to the minus 16. And we get that figure in joules. And then it just becomes a kinetic energy question. Energy in joules equals half mv squared. So to go backwards, we multiply by 2, we divide by the mass of an electron, and we root the answer. And if we do that, we get about 10% of the speed of light. We get 3 times 10 to the 7 meters per second. A very straightforward 5-mark question. Question 12. An airbag is a safety feature used in cars. Nitrogen gas is released into an airbag. The airbag inflates to that volume. The pressure of gas in the inflated airbag is that value. Shows that the number of molecules in nitrogen gas released into the airbag is about 2 times 10 to the 24. And you're given the temperature of gas in Celsius. You're going to use the formula PV equals N little k T. And what we're trying to do is find out what N number of molecules is. So we have the pressure and we have the volume, multiply those two together. And then we divide by little k and we divide by the temperature in Kelvin. And we end up with 2.13 times 10 to the 24, which is approximately 2 times 10 to the 24. So there we go. Now, please bear in mind that with the question starts, show that you know you're going to be using this number in the next question. All right. And if you're not using 2 times 10 to the 24 in the next question, you're probably doing it wrong. So let's have a look at part B. Nitrogen gas escapes from small holes in the inflated airbag. The pressure decreases to that number. Calculate the number of nitrogen molecules that escape from the airbag. And you're told the volume and temperature remain constant. So what we're doing here, because the volume and temperature remains constant, the pressure will be directly related to the number of particles. So the pressure before, we are told, was 1.24 times 10 to the 5, and the pressure now is 345 times 10 to the 4. So if we put one number over the other as a factor and multiply by the number of particles we had before, you can use your number, 2.13 times 10 to the 24, or you can use their number of 2 times 10 to the 24, it doesn't matter. That'll tell you that there's 5.93 times 10 to the 23 left. Now that's left, and now you want the number that escape, so the number escaped is 1.54 times 10 to the 24. I hope that's pretty straightforward. Question 13, a cloud chamber is used to show the tracks of alpha particles and beta particles. These particles ionize the air as they pass through the chamber. Liquid droplets form around the ions. The droplets form visible tracks as shown, and the student makes the following observations. The alpha particle tracks are thick and straight. The beta particle tracks are thin and twisted. Explain these observations. So really, I think there's 4 marks here. So I think 1 mark for each bit. So let's talk about alpha particles first. The alpha particle tracks are thick because the alpha particle is relatively a massive particle, and it's very ionizing. So it's ionizing a lot of things. So as it's going through, it's charging through. It's doing thousands and thousands of ionizations. So that's why it's thick. And it's straight because it has a lot of momentum. The alpha particle is a big, heavy thing, and it's going very fast. It's knocking things out of the way, and it's not really very bothered by its ionizing air. It's not that bothered by the air molecules. It just sort of charges through in a straight line. The beta particles are thin because it's less ionizing, and therefore there are less ionizations taking place. And it's twisted because it has much less momentum. because it's a much smaller particle. It has much less momentum, and it's knocked on its way through, and so it's of a twisted route. I reckon that's a pretty straightforward 4 marks, as long as you say each one in turn. So you're talking about ionization and you're talking about the momentum of the particle. I think you're going to get all 4 there. Question 14. Ice cubes can be made in an ice cube tray. One type of ice cube tray is shown. Each compartment in the ice cube tray has those dimensions, as shown. Show that the mass of water needed to fill one compartment is about that number. Not entirely sure what this is doing in an A2 exam paper. This is really a year 10 IG question, isn't it? I mean, my goodness me. Wow. So what we're going to do is we'll just turn the centimetres into metres and multiply them together to get a volume, and then multiply that by the density of water, and you get 0.0219 kilograms. And again, it's a show that question, so you know you're going to be using this in a minute. Goodness me, 3 marks in year 13 for that. Okay, B. Oh, sorry, that was A. B. All 6 compartments in the ice cube tray are filled with water to a depth of 3.5 centimetres. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5. It takes 12 minutes for all the water to become ice at 0. The manufacturer of the freezer states the freezer can transfer energy at a rate of 110 watts. Evaluate whether energy is transferred from the water in the tray at a rate of 110 watts. And you're given the specific heat capacity of the water and the specific latent heat of fusion of water, which is basically the amount of energy you need to remove to freeze 1 kilogram. So the first thing you do is you work out the mass of water. Well, the mass of water is 6 compartments, so 6 times the number you were given. I would use the number that I worked out rather than their number, so 0.1314 kilograms. That'll probably get you 1 mark. The energy removed to cool it down from 22.5 to 0 would be the mass of the water times 4180 times 22.5. So that would be 12,358 joules. That'll get you a mark. The energy removed to freeze the water would be the mass times that number that you were given, 43,888. And you would add the 2 numbers together. Total energy removed is 56,246 joules. Power is work done over time taken, and you're told that it is 12 minutes. So 12 lots of 60 seconds. When you divide that, it works out at 78 watts. So it's removed heat at less than the claim of 110 watts because the value is 78. So you just need to wrap it up to say, yeah, no, it's less. Sorry, it's not 110. I reckon it's about 78. That's a very straightforward 4 marker. Question 15. Doctors can use ultrasound to monitor the heartbeat of a baby when it is developing inside the mother. The baby's heart was beating at 142 beats per minute. The wall of the baby's heart was moving with that maximum velocity, 22 millimeters per second. Calculate the maximum displacement in millimeters of the wall of the baby's heart. Assume that the motion of the wall of the baby's heart is simple harmonic. Right, so where do we start? We start with calculating omega. Omega equals 2 pi f. Frequency is 142 beats per minute divided by 60. So omega is about 14.87. And you all know that maximum velocity, we don't really have minus sign, minus amplitude or maximum displacement multiplied by omega. So 22 equals minus a times 14.87. Oh, hang on. 22 millimeters per second. Are we allowed to do that? Yes, we can do it in... Why haven't I finished this? Oh, I did. Okay, 22 millimeters per second, and it's 1.48 millimeters. That sounds about right. Is that a reasonable number for a baby's heart? Yes, 1.5 millimeters. The motion of the baby's heart only approximates to simple harmonic. State what is meant by simple harmonic motion. You just write down the defining characteristics. The accelerating force is proportional to displacement. and the accelerating force acts towards the zero displacement mark, always acts towards the center. Question 16. A nucleus of thorium-230 is unstable and decays to a nucleus of radium-226 by emitting an alpha particle. The table shows the masses of the particles involved. So you've been given the thorium nucleus, the radium nucleus, and an alpha particle, all in AMUs. Determine the energy in joules released when a nucleus of thorium-230 emits an alpha particle. So you have to work out the missing mass. So that would be the mass of the thorium-230, take away the radium nucleus, take away the alpha particle. Now, if there was no missing mass, those numbers would go down to 0, but it isn't. There's a missing mass of 5.1 times 10 to the minus 3 U. Multiply that by the mass of U, which you're given. So E equals mc squared, then multiplied by c squared, and you get an answer in joules. 7.62 times 10 to the minus 13 joules. Determine the time taken in years for 90% of the thorium-230 in a sample to decay to radium-226. Half-life of thorium-230 is 75,000 years. Okay, well, before we even start, let's just do a quick and dirty estimate. I think you would agree that after one half-life, it would be down to a half. After two half-lives, it would be down to 25%, and after three half-lives, it would be down to 12.5%. So to get down to 10, the number's going to be slightly more than 3 half-lives. So if I get my calculator out and go 3 times 75,000, I've got 225,000. The answer is probably going to be something in the region of 250,000 years, just as a first guess. So what do? We calculate lambda. Lambda is ln2 over the half-life, so we've got the lambda value. And then we write down the formula, n equals n naught e to the minus lambda t, blah-de-blah. We know the factor, L, so what we do is ln of 0.1 is minus 2.3026, which is equal to minus lambda t, and you just solve for t. Oh, and surprisingly, it's about 250,000 years. So my first guess was about right, 250,000 years, there you go. Easy peasy, 8 marks for question 16. Question 17. In France, scientists from many countries are working together to build the International Thermonuclear Experimental Reactor, also known as a giant white elephant. But let's not go there. On the ITER website, it states fusion is the energy source of the sun and stars. In the core of these stellar bodies, hydrogen nuclei fuse into helium nuclei and release tremendous amounts of energy. This is all true, but none of this is particularly relevant to our ITER because they're not using hydrogen, because we can't fuse hydrogen here. It takes about, on average, 9 billion years, even in the sun, for 2 hydrogen nuclei to come together and fuse and release energy. Anyway, explain why energy is released when hydrogen nuclei fuse to form new helium nuclei. So what we're going to say, you're going to talk about the binding energy per nucleon is much higher, that there is a mass, if you like, there's a mass defect when they come together, and that's the release of energy. Not sure which bits you would say. You could talk about mass defect, you could talk about an increase in the binding energy per nucleon, and you get this release of energy each time 2 nuclei come together. It is hoped that the ITER will be the first fusion device on Earth to maintain nuclear fusion for long periods of time. Okay, maybe it will be. But remember, even if it does, it's not actually producing any useful electricity. What it's doing is simply producing an output of a little bit of energy output, which is probably nothing compared to the amount of energy you're putting in. But again, let's not go there. To achieve fusion in the ITER, a hot plasma is used. The plasma must be at an extremely high temperature and have sufficient density for fusion. Explain what each of these 2 conditions must be met. So it looks like 2 marks each. So why do you need an extremely high temperature? At extremely high temperature, you would have extremely high kinetic energy of the nuclei. They would need to have a very high temperature, so they're traveling very fast, so that they can, here's the killer, so they can overcome forces of electrostatic forces of repulsion, so that they can come close enough together to each other so they can fuse. And they must have sufficient density for fusion, because the chance of them actually getting close together is very small, very, very small. And so to have a decent chance here, you've got to have an awful lot of them together in one area. So there's a reasonable chance of them coming together. So that's why you have to have extremely high density. Not entirely sure where you get 2 marks for the density part. But anyway, I think everyone's going to get 3 at least for that. It's a shame he doesn't actually talk about why it's not actually going to be a practical thing. But anyway, that's for another time. C. The graph shows the variation of binding energy per nucleon with proton number Z. This should be a graph with which you are very familiar. Okay, so along the bottom is Z, and there are some data points on here. And this is binding energy per nucleon in MeVs. In one possible fusion reaction, a nucleus of hydrogen-2, look at it up on the graph there, it's about 1.1, fuses with a nucleus of hydrogen-3. Look that up, it's about 2.8. A nucleus of hydrogen-4 and a free neutron are produced as shown in the following nuclear equation. Determine the energy in MeV released when a nucleus of hydrogen-2 fuses with a nucleus of hydrogen-3. So what you do is you work out the total binding energy. So you're going to basically work out the amount of energy you need to put in to completely pull these things together, and then compare that to the amount of energy released when you have your final product. So 1.1 is the number for hydrogen-2. You times it by 2 because there's 2 of them. 2.8 is the number for hydrogen-3. You multiply it by 3 because there's 3 of them. And then you add those 2 numbers together and you get 10.6 MeVs. And then you look at hydrogen-4, it's 7 MeVs times 4 is 28. And therefore the energy release is the difference between those 2 numbers, 17.4 MeVs. Very straightforward. Okay, so we get to question 18. Question 18 is the narrative 6-mark question that everyone hates. And this is a spectacularly dull question. Wax is heated until the temperature is above the melting point of wax. The hot wax is poured into a bowl and allowed to cool. The graph shows how the temperature of the wax varies with time as it cools. So the hot wax, the liquid wax, is cooling, and between X and Y, the temperature remains constant because there's a change of state and it's solidifying or freezing. And then after Y, it continues to cool down. So describe how the internal energy of the wax changes as the wax cools. You should refer to the energy of the wax molecules as the liquid wax cools and becomes solid, and the solid wax cools. Times X and Y have been included to help you refer to the graph. My goodness me. Okay, so how about defining internal energy first? Internal energy is the sum of the kinetic energy of the particles and the potential energy of the particles. And you can then start talking about the beginning of the graph. So at the beginning of the graph, at the time before X, the temperature is cooling. This is the hot liquid wax cooling. As the hot liquid wax cools, the kinetic energy of the particles reduces because it's cooling down. Therefore, the internal energy is reducing. When it gets to X, it's now at the freezing point of wax. And the line flatlines because during a phase change, there's no change in the temperature. There's no change in the average kinetic energy of the particles. What's happening is that energy is being removed. And this is where it gets a little bit difficult, because what's happening is that the potential energy is becoming more negative. So because internal energy is the sum of kinetic energy and potential energy, the potential energy is becoming more negative, and so therefore the total internal energy is reducing. All right, so potential energy is becoming more negative. That's what I would say. I mean, it's reducing. Potential energy is reducing because it's basically energy is being taken away, and it's going into the form of a negative potential energy. Remember, all potential energies are negative. And then after point Y, there is no increase in potential energy, or when I say increase, what I mean is the potential energy is no longer becoming more negative, and then it's simply cooling down again, and the kinetic energy of the particles is now dropping. So internal energy is reducing all the time. At the beginning, it's the kinetic energy that's reducing, then the potential energy is becoming more negative, and then the kinetic energy is reducing again. I think that will get you most of the 6 marks if you haven't fallen asleep with boredom. What a terribly dull 6 marker. But anyway, there you go. Question 19. A student hangs a mass of 0.22 kilograms from 2 identical springs as shown. She displaces the mass vertically, and the mass oscillates with simple harmonic motion. The mass is oscillating around the point of equilibrium. It's not oscillating around the point at which the springs have 0 stretch. The student measures the time t for the mass to complete 30 oscillations. She repeats this measurement. Her measurements are given in the table. So 13.65, 13.70. The springs are taken from a box labelled K equals 21 newtons per metre. Deduce whether the value of K stated on the label is correct. Wow. Very straightforward. Okay. So you know that for an oscillating mass on a spring, the time period is 2 pi times the root of the mass divided by the K value. So if you work backwards to get T, so you know, what do we do here? 0.55835 is T. I've taken the average of the two. And why did I divide by 30? I must have done that for a reason. 1 moment. Goodness. Oh, because there were 30 oscillations. Blimey, brain going. So I averaged these two numbers, divided by 30 to get the time for one oscillation, 0.5583 seconds. That equals 2 pi, root 0.22 over K. Solve for K. K is 41.8 newtons per meter. But you need to know that because the springs are in parallel, the stiffness adds up. So therefore, K should be about half that value. So we're saying that if they were 21, the K value would be 2 times 21, which is 42. So the predicted value of 42 is very close. So it does appear to me to be correctly labelled. That's it. So it's correctly labelled. Looks good to me. B. The student attaches the mass to one spring and holds the other end. She sets the mass into oscillation by oscillating her hand vertically as shown. The student increases the frequency at which she oscillates her hand. She keeps the amplitude of oscillation of her hand constant. She observes that the amplitude of oscillation of the mass increases to a maximum and then decreases. Explain this observation. Okay, so this is a question about resonance, obviously. So what's happening is as she increases the frequency, there comes a point where, and these are the words you would use, the frequency of oscillation, or the forced frequency of oscillation, matches the natural frequency of oscillation. And at that point, resonance occurred. Resonance occurs in which the amplitude is maximized and there is the maximum transfer of energy. A little bit later, she changes the frequency again. She's increasing the frequency, so it's no longer at resonant frequency, and the amplitude of the oscillation therefore decreases. So it's a straightforward question about resonance. You just have to use the right words. The student makes the following conclusion. As the frequency is increased, the amplitude of the mass increases to a maximum, so energy conservation does not apply to this situation. Explain whether her conclusion is correct. That's a rather odd question, isn't it? Okay, so when she says energy conservation does not apply, Obviously, that statement is ridiculous because energy conservation always applies. It's just that it may leave the system. It may just go elsewhere. So what's happening here is that the energy of her hand is being, some of the kinetic energy that she's putting into the system is being transferred to the kinetic energy of the mass. So energy there, but there's also obviously some dampening, some friction going on in there. Some energy is being dissipated to the surroundings. And then it says the amplitude of the mass increases to a maximum, so energy conservation does not apply. Because she's only talking up to that maximum point, I think you can just say her statement is incorrect. A maximum amount of the energy of the hand moving is being transferred to the mass oscillating. Some of that energy is being dissipated to the environment through thermal energy dissipation. So energy conservation always applies. So her statement cannot be correct because it's just not true to say that. It's just that you sometimes don't, your energy accounting doesn't work because you've lost some energy to the environment. It doesn't mean that energy isn't being conserved. It is being conserved. It's just being dissipated. I'm not very happy with that for 3 marks. Anyway, question 20. The Hertzsprung-Russell diagram, the HR diagram for a star cluster is shown. Luminosity, it does say temperature in Kelvin along the bottom, that's interesting, at a scale to the horizontal axis. So you know it's a reverse temperature scale. Not sure where you get the 2 marks for, maybe 1 mark for just showing that it's reversed, 1 mark for showing. So roughly it will be on the left hand side, it'd be about 30k, and just before the T there, it would be about 3000k. So from 30k to 3k. And in the middle, where luminosity 1 for the sun, that would be about 5,500k. I'm not sure how many you would have to put in. I think if you started with 30, you wrote about 5.5k where the sun was and 3k over on the right. I'm sure you'd get both marks. Explain how this HR diagram shows that the star cluster is not a young star cluster. You should refer to groups of stars and their positions in this diagram. Okay, so it's not a young star cluster. How do we know? And how many marks? We've got 3. So we've got to name the areas. So what would you do? Up here, we've got some red giants. It's not young because there are plenty of red giants showing. Red giants would only occur after a main sequence star has come to the end of its life. And that's obviously going to take some time. There are lots of red supergiants at the top as well. They would have been the first to go. But in order to get the red giants, there must have been some considerable time so that main sequence stars can evolve to red giants. And also at the bottom, down here at the bottom, there are some white dwarfs, which means that some red giants have gone all the way through to white dwarfs. So it's clearly not a young cluster because you wouldn't expect to see any red giants or white dwarfs in a young cluster. I think that's enough for 3 marks. C. In the earlier 20th century, Edwin Hubble observed the Andromeda Nebula. He saw stars similar to the stars in our galaxy. One star he saw was a standard candle known as V1. Describe how measurements of this standard candle could demonstrate that the Andromeda Nebula is not a nearby star cluster. Well, I think you're probably going to get 1 mark for just defining what a standard candle is. A standard candle is an astronomical body of known luminosity. If we rearrange the formula, we get distance squared is luminosity divided by 4 pi intensity. We know the luminosity. So for standard candles, we know the luminosity. And we can measure the intensity as seen here on Earth. We know what the size of our telescope is, and we can just work it out. So if we divide L by 4 pi I, it gives us distance squared. And if that number, distance squared, if it was a nearby star cluster, we would expect the distance to be of the order of perhaps hundreds of light years. But if it's not a nearby star cluster, we'll probably find that that value is in the order of 2 million light years, because Andromeda is about 2 million light years away. So it's vastly further than nearby star clusters. Not entirely sure where you're going to get all 4 marks from, but talking about standard candles, it's not a particularly well phrased question. But anyway, I've done my best. Hopefully you'd get 4 for that. And I think we're moving on to the last question, question 21. Ross 154 is one of the closest stars to the Sun. The graph shows how the power radiated from Ross 154 depends upon wavelength lambda. So you've got lambda along the bottom, and you've got radiation power. Show that the surface temperature of Ross is about 3000 Kelvin. So we know, read off the graph, look for peak wavelength, pretty much 850 nans. So 850 nans times the temperature equals the constant, 2.898 times 10 to the minus 3. So T is 3409, which is about 3000. There you go. I'm going to use 3409 for my number later on. You know you're going to use it because it starts with show that. So you know you're going to have to use 3409 in the next part. A website states the luminosity of Ross 154 is less than half of 1% of the luminosity of the Sun. Evaluate whether this statement is correct. You are told the radius of Ross 154. You're told the luminosity of the Sun. You're going to use the formula that's given to you, L equals sigma squiggle multiplied by cross-section surface area times T to the 4. So 4 pi, you have to work out the area of Ross. You're given it in meters, the radius, so it's 4 pi r squared multiplied by 3409 to the 4th. And when you do all of that, you get 1.34 times 10 to the 24 watts. Half of 1% of our Sun would be 1.915 times 10 to the 24. And so you would finish, yes, it is less than 0.5% of the Sun. There you go. That's a very straightforward 5 marks, isn't it? Scientists have observed an Earth-type planet in orbit around Ross 154. The radius of the orbit is given. Calculate the time for this planet to make one orbit of Ross 154, and you're given a bit of data. So you will use the most important formula in astrophysics. Big G, big M for any orbital system is a constant. That's the mass of the thing in the middle times big G. And that always equals omega squared r cubed. So you will divide big G times big M, which you are given, and you will divide that by the radius cubed. So you'll turn the radius into meters and cube it, and that'll give you omega squared. You'll then square root omega to get 2.7 times 10 to the minus, sorry, you'll square root that number, and you get omega, 2.748 times 10 to the minus 6. Omega is 2 pi over t, so 2 pi over omega will give you t, about 2.2 million seconds. I don't like that, I've turned it into days. It's about 26.5 days. That is the last question, and it's not very demanding at all, frankly. So I think quite a straightforward paper, a rather dull 6 marker, a little bit of talking about stuff, but otherwise I think pretty straightforward. Okay, thank you for this quick walkthrough. I hope you found it useful. Look forward to posting some more. Thank you and goodbye.